Yes, whenever you want. So,
Okay.
Andrei, first of all, thank you for being here, and then you can start.
Hi guys, how it's going? Well, today I'm going to talk about SPEC CPU 2017 and some use cases that I came across when I was doing my PhD and also when I'm advising some students in Cefet MG. So I hope this will be useful for us. Well, there are actually not so many cases, but I give a little bit of introduction, then some how to install, how to configure, and how to validate the experiments. And then we get into what the presentation is supposed to do. That's a little bit about profiling. So we'll see how to do dynamic profiling and how to do feedback directed optimizations as well. So first for introductions, SPEC is actually a non-profit organization that stands for Standard Performance Evaluation Corporation. And it is used, it creates benchmarks that can evaluate the performance and energy efficiency of computer systems. And they have a plethora of benchmarks available, like for cloud, for CPU, for graphics and workstations, high performance computing and machine learning, things like that. But here we are only interested in this SPEC CPU. So SPEC CPU has a long history as well. Since '92, they launched some benchmarks, some versions, and then from 95, then 2000, 2006, and 2017. I did my master's in 2010, and people back then used to we used to see a lot of papers using SPEC 95, a lot of papers doing SPEC 2000, and since it was kind of new, not so many about 2006. But even though it's used a lot in compilers evaluation, nowadays we are in 2021, and we still don't see as much papers using SPEC 2017. We also see papers using SPEC 10, 20, 2006. So here we are really interested in the latest version, that SPEC CPU 2017. It's important to tell that SPEC actually requires a license to be used, but Fernando and WFMG has bought a license, so we can use in our research group. So SPEC CPU contains a set of like CPU intensive suites for measuring and comparing compute intensive performance. So a set of benchmarks that can stress the system processor or memory subsystem. It can be used to evaluate the cache subsystem, and it's quite used in compiler research. It has specific for SPEC 2017. We have 43 benchmarks that's organized into 4 suites. So we have SPEC speed, that we have some benchmarks for integer calculation and floating point calculations. And speed is usually meant for benchmarks that have threads. So they run very fast with many threads. And we also have a spec rate, also for integer and floating point, that usually you should only use only a process. So this is useful for measuring the throughput of work per units of time. So we are just measuring time, and the one before is used to complete a single test. So we have many threads, and we want to see how it does to complete it. So overview of the spec. So it's divided in these 4 categories. So the first one, int speed, has 10 benchmarks, fpace speed 10 programs, int rates 10 integer, and fp rates 13 floating point benchmarks. We usually use this short name when we are doing simulations. We will see right now in a little bit that we use int rate. And there's something to say about the metrics. So they have this kind of metrics that they call base and peak, and also where they also can measure energy and also in base and peak. And they do this specifically for this reason. Base, you should compile all the benchmarks using the same set of compiler flags. PEEK, on the other hand, you may vary. So maybe you want to stress out that one of the benchmarks should maybe the order of compiler flags could be better for one benchmark, so you can exploit this kind of things for PEEK. But for base, we should stick to the same flags. So this is more like a philosophical distinction that they use internally. So I just put here the benchmarks for spec rates and spec speed for integer. So they usually have like, this is that like integer benchmark. So they have compilers, interpreters, video compressions, some artificial intelligence things and things like that. And the important thing to notice here is that the benchmarks are written in C, C++, and Fortran. And this is also happens for the floating point benchmarks. So they have some benchmarks about physics calculation, molecular dynamics, ray tracing, and things like that. So it's quite, how do I say, wide range of applications that we can stress compiler optimizations. So I would like to talk a little bit about installation. So the benchmarks are written in C, C++, and Fortran. So we should have these compilers available in our environment. In Ubuntu, I could install it with build essentials. So with this, I can install GCC and G++. And for Fortran, we are using G-Fortran, and we can install with apt-get as well. So you should have these 3 compilers available. But you can use other compilers if you want. They have like configuration files for ICC, right, the Intel compiler, and then for CLang and things like that, other compilers. So you just need compilers for this language. So the next thing that we need to install the spec. So the first thing is to mount the ISO image. So sometimes if you have root privilege, you can use the command mount, but you should use sudo to use this command. Using the IO, the disk image, you can mount it. And if you don't have root privilege, there is an utility that's called fuse ISO that you can mount the disk image easier. But the system must have this tool. So I put these 2 options here. Then there's an install script after you mount, let's mount in the temp ISO directory. Then we can call the install shguide script. So first we enter the directory, then we can. I should make the order different here, but like we need to separate some parts in our system for where the installation will go through. So I will put in my home directory with the benchmarks name. And then we should enter the directory that we just mount and call the install script. Then the script will ask us, where do we want the benchmark to be installed at? So we can add this directory like I just created, and with the spec name, something like this. And then he will just print where we are installing from and where we are installing to. If this is correct, you just say yes, and the system proceeds installing in this directory. I will not go through here because it takes a little bit of time, but it's just straightforward. Just 2 questions and you're set to go. Then just remember to mount the image. If you have root privileges, you can use a mount. And if you don't have, you can use fuse mount. So you have 2 options this as well. I forgot to mention something here. No, I think I'll say later. Yeah, I will remember later. So after we install the SPEC CPU, we can find the root directory in some like where we install it, and then they usually configure this variables that we can use. So this in Unix world and this in the Windows world. Well, inside this we have the bench spec, the directory inside where we install the spec. and usually this directory contains the benchmarks itself. So you have the CPU and the benchmarks are in there. You have bin that contains the tools used by SPEC and scripts to run and report on the suite. The configuration files on config, some documentations in doc. Results is where our logs can be found later. So we use this path. Temp for some temporary files. Source of these tools. Well, within each of the individual benchmarks that we can find directly, we have the following structure. The benchmarks are usually named with 3 digits number and then the benchmark name. For example, GCC in spec rate integer is 502.gcc, something like that. So in this directory, we have a build directory where the spec will build the application, the program. We have some data folders that we have for all data that are used for all runs, and then for reference, for tests, and for training. Docs, the compiler version, they build in the spec, and then they copy to this X directory. And then we have the run directory where we will run the suite. So this is a step that I really don't understand why. So once they build, they copy to this exact folder, and then they copy again to the run folder. So to run the benchmarks there. I really don't know why. And then we have some directory about spec metadata and the source of the benchmarks. So just a little overview. Okay, let's go into configuring spec now. So the first thing, we need to use, like the configuration file is quite complex. So they recommend us to use like a template. So first thing, let's enter in the benchmark directory we just installed. And let's choose some example configuration files. So here I'm copying GCC for x86. Let me sorry. So I just installed it beforehand. So we have the config directory, and we have many examples here. So you have GCC for Arch 64 and things like that, Slang. We have a target for Mac OS when I usually, when I was doing work in my computer, I usually do this one. But since we are using a Linux server here, I'm using GCC 86. So I'm just copying it. To something like. So
Andrei,
you
can you move the window just a tiny knot to the left?
Sorry?
Now a bit to the right.
Like this?
Yes, that's perfect.
All right. So I just copy the config file, and then we are usually working with some like specific flags for our work and things like that. So we usually need to copy all these things we can do on the fly, but I usually prefer to do this on configuration files. So we also want to copy some compiler flags to our own, to build upon our config flags, a compiler configuration flag. So I will also copy this. CP flags, GCC, like flags, GCC. We will see how this works in a little bit. The directory copy the base template files. Like I said, some configuration options can be overwritten at runtime. And unsupported compiler flags can be included for a portable run. So we need to do this here. So the second thing, this is actually optional, but I put it here because probably we are going to use something like that. So if you're going to use a specific compiler flag, we need to add this flag to the configuration files for the compiler flags. So here I choose the minus NoPy to do for the compiler not to do position independent code. So this compiler flag is not supported by SPEC, like built-in. So I just created this entry in the file. So I just put, I kind of followed the way they did things and just add a new entry. So let's do something like that. I try to, like for my OCD, I try to put it near the flags like they are kind of in the alphabetic order. So MV SI3, MVIS 3. So I will put between, since it's no pi, I will put between M and O. So I just copy this flag, put in here. So I name no pi. They have some regular expression. They know that this is a flag. And then we can have some text that can be output to the report. So this is no position independent code, something like that. Save it. Then we can proceed to the final step, that is to configure the configuration file. So we are going to edit the config file. So here the first thing is to change the flags URL to this new compiler flags file that we just created. And like I said in the beginning, we have two metrics that they call tune inside here. So it's base and peak. Let's choose base now. We're doing the same compiler flags for now. Well, then we need to choose how many CPUs to use. So we have a distinction here. For we have int rate and FP rate, and int speed and FP speed. For int rate and FP rate, they are a standalone application. They do not have threads. So this configuration of copies is how many instances of this program we want to run. So in this, like the default configuration is to run one copy, like one program simultaneously, but you can change this to anything you want. In the documentation, the official reports, they can have this number as big as 25, something like that. And for the others, int speed and FP speed, we can actually choose how many threads we can use. They are programs with threads, and we can set how many threads we want to use. But for this type of benchmarks, we only have one copies. We cannot have copies and threads at the same time. We can only have one copy and many threads. And in this case, we have many threads, but many copies, but just one thread. So it's kind of distinct how they did this too. Well, then the compiler flags, we need to find out where our GCC directory is. So in here, my GCC is in /user/bin/GCC. So we put the directory without the bin. So here, just set this up. And then we are going to use our compiler flags. Here again, we can see we are using base, the same as tuning from above. And here's the optimization flags that we use to compile. So I'm including optionally the NoPy optimization in this run. So I just put it in here as well. Then after this is configured, let's try to do this. I don't think we can simulate it, but just so you can have a grasp of how is the configuration files here. So it's a little bit big. You have some explanations and things like that. We change this one. So keep it base.
But
How many CPUs I just tell me?
I'm fine, just a bit redundant. Why do you have to add the flags into the XML file and then back again into the configuration file?
I will explain this in a little bit. Okay. Otherwise, they will claim that it's an invalid run.
Okay.
I will go there. Okay. So I just here gonna put USR. user. Then they have some special flags like for portability, and they have things like that, but we don't need to worry about it. They have some specific flags for speed for like OpenMP and things like that. So here is our default base optimizations, and we can add the NoPy here. Okay, that's it. And we can proceed to the simulations. So when we are validating, we need to first like loading an environment of how the stack will set up some variables like shell variables and other setup configurations. So we need to load the simulation environment. We usually do by loading this shrc config file. So just load it, and then we can run the CPU. So we will tell, this is our configuration file that we just built. In case for reportable runs, we need to use at least 3 iterations, like execute each benchmark 3 times. Actually in the documentation, they claim that you can also do 2. So a reportable run can have 2 as well, but 3 sounds like a better number here. And then we say that's a reportable run. We want to, you will see the difference in a little bit. So just to make it reportable. And then which benchmark do we want? Remember that we have like that 4 categories, like int rate, int speed, FP rate, and FP speed. So here we are just selecting a collection of 10 benchmarks. We can also choose other groups like FP rate, a specific benchmark, in this case like 502 GCC. But if you choose that, it's not reportable anymore. It's just reportable if you at least execute a group. Or you can also execute a superset. Like if you choose spec rate here, it will simulate int rate and FP rate. And the same thing for spec speed. So it will simulate spec speed rate and int speed and FP speed. Or all will simulate all the 43 benchmarks of the 4 categories. So just this is a default run for the simulations. And here we have an action that's called validate. So the default action is validate. There are others that I'm not going to, but you could just like, if you just need to use the compiled versions, you can only build and not run and things like that. So validate is to build and run, and sometimes train. We will see in a little bit. There's specifically a problem with the benchmark that is called CAM4 in FP speeds, that it uses a very large stack. So we need to configure this flag for ensuring that we have enough stack memory for it to run. So I came across this problem, and they also have this in the documentation. So it's quite useful, quite important. I also marked some links here, down here. So I hope this presentation can be useful later. So in the documentation, I point out the important things that we need to look at. So here's the documentation for run CPU, and this documentation is actually very complete, quite complex. So when we run the spec, they generate, I guess I did that pretty fast, but they generate in many formats. And one of the formats is a PDF file. So you can, if someone could ask for your, how do I say, the artifacts of your search, you could point out to this kind of file that is quite complete as well. So here we say that we execute the int rate benchmark using base, not peak in this case, and we have the numbers here of the 3 runs, so 1, 2, and 3. They also mark the one that's small, the median time. Well, if any problem happens in the simulation, we have an invalid run. So it like pastes this enormous warning in the configuration file that just states this is an invalid run. So that's the problem. Like I use the NoPy optimization, but if I didn't put it in the compiler flags, it would mark me as an invalid run. But not everything is lost here. If this kind of problem happens because of flags, we can recover the report with the CPU tool that's called raw format. So we can add this flag post-mortem and then regenerate the report. So it's something you can do as well. And the documentation is here in case anyone wants to see. So the simulation takes a long time. So I just generated here. So you guys can see, I try it without the flags first, and then it puts this enormous, gigantic warning. And then he says, U1 was marked invalid because one or more flags in the unknown category, because it has one or more flags in the unknown category. You might be able to resolve this problem without rerunning your test, and then they point out where we can do this. So if we go here, this is the times we collected. And then back here, they say some configurations, how do you compile and things like that. And here are the basic problems. So we used the NoPy, but we didn't put it in the compiler flag. So it's like for SPEC that you're running on a no optimization, things like that. So if you want a valid report, we need to add this to the compiler flags. And if you do that, we can then regenerate this report with a valid report. And then we can see here that like someone using this report can see that we really use the NoPy optimization here. So this is quite interesting. Oh, sorry, I just opened WhatsApp. So another interesting thing, sorry guys, is that this would be hard to extract information from the PDF file, but they also report in textual file. So they also put something like SPEC 2017 iterate.txt. If we open it here, let me go to my desktop. Sorry, my computer's kind of suffering. This was an invalid run because I executed without the NoPy, but the idea remains the same. So between this this marker and this marker, we have all the simulation side. Like for XZ, we execute the first one was like this time in seconds. And then they put the median here, so 563. Since this is in textual file, we can extract this information quite easily. Instead of relying on like copying and pasting, things can get, you can have problems. It's very easy to create a script for this. So I just mark the beginning and the end of this section, and then I filter for the ones that starts with 3 digits. So like every benchmark starts with 3 digits. And then I just, it's okay. I put a space here, and then I change to comma later. So things like that, and I can generate a CSV file that can be used to plot a shard, for example. So this is quite useful. Well, now we get into the real meat of what I would like to talk about today. It's a little bit about profiling. And in the context of SPEC CPU, we are actually interested in two types of profiling. That's dynamic profiling, like simulating a program, monitoring its execution. We usually do with the dynamic binary instrumentation framework at DBI, PIN and DynamoRio. So we can evaluate the behavior like a pass in this type of DBIs. And also with feedback direct optimizations. Like this is usually compiled in two phases. In the first phase, the compiler adds some instrumentation. For example, for GCC, it will use the flag fprofile generate phase. So this will generate a binary with instrumentation that once executed collects runtime information like statistics, and then in the second phase we can use retrofeed and this information file back into the system with this flag fprofile use. We can use this feedback direct optimizations, but I actually use a different one. But if you choose to use this kind of FDO, in the compiler flags, this is supported already. To the flags, it's Andrei GCC, and we search for fprofile use. So it's already covered here. So we have fprofile generate and fprofile use. So if you want to use this kind of flags, they are already included in the configuration files. So in the first instance, in the first case, we want, like if you want dynamic profiling, I have some bad news. No, actually before the bad news, to perform the dynamic profiling, like imagine that we execute the benchmark with some, like invoking this program with some arguments. If you want to use a DBI like Valgrind, for example, we need to prepend this command before the actual benchmark. So for in case I'm doing a little propaganda about my tool that's called CFG Green that we did in the PhD here in UFMG, and you can find the link here. So if you want to run the SPEC with this kind of you need to prepend this command. But now the bad news, I actually couldn't find a way to do this easily in SPEC. I'm not an expert, actually. My co-advisor, that's José Nelson Amaral, is part of the committee of SPEC. I've talked to some, I visited him in Canada, and I did talk with some of his students that had some experience as well with SPEC, and they also didn't know how to do this. But there are some ways that we can do this kind of manually. So instead of using validate in the actions, we could just build and then run like manually. But that would make this process very troublesome. And I actually enjoy using SPEC for the automation. They have a lot of built-in scripts that do all the magic for us. But specifically for this case, I couldn't find a way to do this. So I actually did I don't know if this is like valid in the point of view of SPEC, but this was the easiest way that I could think of. So I actually created a patch and patched the SPEC installation to support a new flag that I called prepend. So we can just enter this directory, download this patch, and then apply it. So we change the scripts, including run CPU, and then we can use run CPU to use this flag. So I included this prepend minus prepend flag that we can pre-append a command actually before the benchmark program to be executed.
So Andrei, you are saying that whenever you run this, this command will be in the command line before whatever would come naturally.
Yeah, exactly. So you can do anything before it.
All right.
So this is, for me, is the easiest way to approach this problem. Like we could use some shady things to make this work, but it will be so hard to do that does not pay out. So for me, the easiest thing was to actually patch the spec. I created a tutorial. You can click it here. So just saying that we create a patch and things like that. So I will also not execute this. This is just straightforward. Just load the environment again, and then run CPU, and we can collect the statistics for this run. Well, the other workflow is the feedback-directed optimizations. This one is actually supported in SPEC. I actually, since I did this workflow before, like patching SPEC, I thought when I needed to do feedback-directed optimizations, I could use something like that. So I began to try to write a patch to do an FDO. Then I noticed that in some parts of the source code, the scripts, they were like FDO this, FDO that. So I kind of, well, there's really something here. And actually it's supported natively. So instead of running that GCC workflow with fprofile generate and fprofile use, let's do something that Angelica has worked on, that is using Bolt. So how does Bolt works? We need to download. I just downloaded a program, a test program here, and we need to compile it. I compiled it here with NumPy. This one is not necessary, or is not mandatory, but this one is. This one is a linker flag that includes within the code some reallocation information, like code reallocation. So this is required for SPEC, for Bolt. So Bolt, for the people who don't know what Bolt is a link optimizer. So after the program is compiled and linked, it can be optimized in the binary level. So in here, we need to compile with this flag, but once the compiler has, the binary has reallocation code, we can use both without a problem. So this program test that I just downloaded here, it just sorts numbers that are passed in the command line. So here I generate 10,000 numbers in sequence, and then sort them, like randomize them, to sort them. In case of both, we need to collect information. We can use perf here to do that. So perf can use some processor counters and things like that to collect some runtime information about this execution. And in this case, let me just go through it. So first we download, then we compile with reallocation. Then I just executed 3 times just for us to, just to show a workflow here. Then I randomized 10,000 numbers, and then we use perf to collect data. So in here, we are also using this like a command before our command, but this will be supported in a short. Then we can, so perf generates some information in their own specific way, so in their own specific format. And then we can use a script from Bolt as well that's called perf to Bolt that translates this perf data to a data that is more useful to them. So they call F data. In here, I'm generating like we are doing 3 runs. So I'm generating run 1 dot data, run 2 dot data, run 3 dot data, and then the same thing for f data. So run 1 f data and things and so on. So we need to the binary and then this data. Once all these 3 data for this workflow are done, we can merge all the information collected in these 3 runs in a collapsed format. So we call here all f data. So to optimize this binary. So if we load the original binary, we compile it with, we generate an optimized version, and here we include the merged data of all the 3 executions. So I'm just selecting a more complex workflow so we can use feedback right optimizations. So how can we apply this workflow to SPEC? To add this flag, so we don't get an invalid run report file. So we are just using this. This is a little bit different because it does not have the F name here, but I just use some alike. So this is a linker flag. So I just copy this one to here and just change the value. So it's quite straightforward as well. So we can just do this to make reportable runs. Then we need to start updating our configuration file. So for FDO optimizations, we can only do that in peak metric. So we need to change from base to peak here. The peak tuning flags, we need the default peak. They usually have this flag, a comment, not comment, because they use the same flags as base. But in here, we want to comment or remove this line. So I just comment here with the hashtag. Then we add the optimize, and here I just copy the optimization flags from base, and then I included the linker, the bolt optimization that's required, the compiler flag that's required for bolt. And I had to also copy this section here because if we don't, the benchmarks just don't compile. So we need to compile all of them with the int rate and speed with these 2 flags. They have this for base too, so I just copied. So let me just find it here so you can see. No, not here, sorry. No, right. So they have this for base, so you can see the section. So in default base, they have this. But if you go to peak, they don't have this. So this is the peak section. And by default, they use just the same flags from base. So I comment this line, and then I copy the optimization and also that extra flags to do this to work. Okay, so change of tune, comment, copy, and then add the new flag, and then copy the section as well. I remember to, if you copy, it will say base here, you need to change to peak as well. All right, so here is the built-in part. SPEC has a built-in support. So usually the framework is to build a program with instrumentation that fits FDO workflow. Run the sample with a training workload. So we don't want to run the optimizations in the same environment, in the same arguments as the full program. Like we want to train, we want to like collect statistics with a small sample of workload, and then use the sample, the collected profile later with the modifier program in a more complex run. So we usually like to separate from training and for validation here when using FDO. And this behavior of like doing FDO in SPEC, they have 4 ways to do this: with pass and make variables, with FDO shell options, with feedback config file options, and with some run CPU options with minus feedback. But we here are only interested in this one. FDO shell options will be more powerful to us. So some of the shell options that we can use FDO pre-0, that this command is executed before starting the FDO series. Pre-n is before executing pass n, so I can have as many passes as I want in this FDO workflow. We can just need to change this n to something, 1, 2, 3, and things like that. So pre is just before executing the pass. Pre-make is before compiling. This one is for in the compile phase. This one is after compile phase, and this is after run. No, this is the run phase, and this is after run. So the awesome thing about SPEC that we can use these variables, and these are like shell scripts. So you can use environment variables as we wish. We will see a workflow. And for our purpose, using both, we will only need this three of this. So we will do some cleanup, we do some run, and then we do some post-compile things, post-run things. Also some interesting variables that we can use like in this script. Usually base X will be some parts of the execution names like EBM -R, _R. The benchmark name includes the 3 numbers. The bench name would be just, no, sorry. The base X is like this. The bench name is just the benchmark name. The bench num is just the number. The comment is like how we actually execute this code. So this program with these arguments. The comment X is just the name of the program without the arguments. Iteration is the number of the iteration, and tune is the number if you are using base or peak. So we can use these variables to workload, which workload. So some variables here. And we can now is the time that we do I forgot to change here. So I need to comment this line. We are actually just adding these lines afterwards. So here we are doing some cleanup. We are just removing some like previous data and F data, like this one is from perf for both. And then I'm creating like a first data. Since our training model, they can have many runs, I actually don't know how many runs I did to merge the data afterwards. So I did a hackish thing here. It's like I just changed the empty name to a previous. I run perf in like the benchmark data, and then I generate a current. So now I have previous and then current, and then I update to the file, to the original file. So this is just a way so we can merge as we go. Like for every run, we are merging at a time. And then I just delete these intermediate files. So we are here just running, like you can see, we can use these variables, really like a shell script. Like this is a comment, this is a comment, this is a comment. I'm using the benchmark name here, the comment here, the program name here, and things like that. And after we execute and after we run the training set, we can do some post optimizations. And then here's where we call both. So I just copied the original executable file, like with a suffix. And then I optimize both with the like since it will be used later in the complete run, I just changed the default compiled version to this optimized version. So in order to do that, I just back up the original one and use this original one as base for the optimized. And then we can load the F data that we collected. So this is quite scripted. Can you see? We are just doing if statement here. So I just did this because sometimes if perf does not collect enough information, this file can be empty in the end. So I just test if it's not empty, we can do this kind of thing. So we can use a compiler flag that's called fake, that we can simulate what we are actually doing. So in our script, the variables, but once we are running, we can see actually what we are using. So the benchmark name is substituted by the real name for, like, for example, if I want to run GCC, it will be changed to GCC. And then here is the section that we are really using the instrumentation with perf, converting to both formats, and then merging, and then merging. And in the end, we just optimize the final binary. So once the binary is optimized in here, now the optimized version will be used in the final run. So after that, we just need to run the same way we did before, and we'll be using FDO now. Like we can see here, in case of FDO, we use base and peak. And since FDO must use peak, they also compile for base. So you have the two options here. Guys, sorry, it was a little bit rushed in the end, but just show how powerful it is to use SPEC to do this kind of workflow. I think it's quite useful.